video, I'll look at how we go about solving problems with simple harmonic motion. Right, so first of all, you have to determine whether something is simple harmonic motion. That's pretty straightforward because exam questions generally tell you. But remember, you're looking for the force to be proportional to the displacement or the acceleration to be proportional to the displacement, but towards the equilibrium position. Now, if you look at the equations that we've got, and I will step back, all of these, all of these, to determine displacement, the velocity, the acceleration, the one thing that you're going to always need to find out is what the angular velocity is. I mean, you need the amplitude as well, but you can just measure that easily. The difficult bit, or the bit that's a slight challenge, is how do you find the angular velocity of, say, a mass on a spring that's oscillating up and down, or the angular velocity of a pendulum swinging back and forth. Because remember, we're thinking of simple harmonic motion as just one component of this sort of imaginary circular motion that's taking place somewhere. So you can't go and see the circle and measure the number of degrees it moves through, the number of radians it moves through in a certain time to determine the angular velocity. So how do you do it? Well, if the thing's moving, it's really straightforward, because although we can't measure omega directly, which is what my terrible writing says here, we can often measure the frequency or the time period of the oscillation. There you go. Easy if you can measure the time period. Because you just measure the time period, substitute it in this equation that we talked about earlier, and Bob's your uncle, you can solve any problem. So, first thing is, confronted with a question about simple harmonic motion, try and identify what the time period is. If you can spot that, you can apply all of the equations that are all given to you on the equation sheet, because you know what omega is. Sometimes it doesn't give you the time period, it gives you the frequency, but that's not beyond you because frequency is just 1 over the time period. So that's the easy thing. Where it can get a bit more challenging is that sometimes they show you things where they don't tell you the time period. So you have to approach it a different way. I mean, they have to give you enough information, but there's something else that you have to do. And generally this will involve springs. The examiners like this because it connects very, very neatly with the stuff that you did in year 12 with Hooke's law. I'll show you what I mean. Whoops. Keep saying whoops, sorry. Right. What if you can't measure the time period? Now, say I've got this mass suspended on this spring. It's obviously extended, and I say to you, you are not allowed to touch it. I'll let you go up to it with a ruler. I'll let you measure things. I'll let you measure the extension of the spring, all that sort of stuff that you did in year 12 with Hooke's law, but I'm not going to let you actually move this. And then I say, well, just with that information, could you determine the time period of the oscillation? And at first glance, you'd think no. But then you have to remember that all of the things that we've studied are all true. Okay? So the fact we've got an equation here for acceleration is equal to minus omega squared x, that's going to be true when this starts moving. But also, mechanics from year 12, F equals ma. The force on this is going to be proportional to this acceleration, and it's going to be related to the mass as well. And going back to materials in year 12, this spring's still going to obey Hooke's law. F is going to equal kx, or as we now say, F equals minus kx. So how could we use all of this to work out what omega is equal to? Have a think for a second. Okay, so I'm going to show you how I would approach it. I've got a little version of it up here. I'm going to start with what I know about simple harmonic motion. I know that simple harmonic motion tells me the acceleration is equal to minus omega squared x. Then I'm going to write down the other things that I said a minute ago. So one of the things I said was Hooke's law, F equals minus kx. Always true for a spring that's not extended beyond its elastic limit. Not quite true, but almost true. I'm also going to jot down Newton's second law, F equals ma. Now, I'm going to rearrange Newton's second law now to tell me what the acceleration is equal to. The reason I'm going to do that is I'm going to sort of think up here and go, oh, okay, this is telling me about how acceleration is equal to something. So Newton's second law, what's acceleration equal to? Obviously, A equals F over m. But I know from Hooke's law that this F is equal to minus kx, isn't it? So I can substitute that in and I get this. Acceleration is equal to minus kx over m. I'm just going to get a pen because I want to draw your attention to something that, look, acceleration is equal to blah, blah, blah multiplied by x. Omega squared must be the same as k over m. Might be more obvious if it's written out more neatly, so I'll have it on this slide here. So look, this is what I got by combining Hooke's law and Newton's second. A equals minus k over mx. This is what our simple harmonic motion equations tell us. Therefore, k over m must be omega squared. Now this is brilliant, because now we've got a way of determining what the angular velocity is going to be without even seeing anything happen. If I give you a spring and say, find out the spring constant of that spring, and you can do that, you just hang a mass on it and measure the extension and use Hooke's law. And I then say, right, well, tell me what the angular velocity of its motion will be. You just divide the spring constant by the mass of what's hanging on the spring. That tells you omega squared. And then if you've got omega, you can find out what the time period's going to be. And I think that, I mean, it's a shame that we're not in class to try this, because I think it's quite remarkable that I normally have it set up in class. I have a spring with a mass on, and I say, work out what the time period will be. And it works beautifully. So this is the thing that I think you should make note of the most. This is how it gets challenging in simple harmonic motion. So one idea is determine angular velocity from the time period if you know it. If you don't know the time period, you can get the angular velocity by finding out the spring constant, if it's a spring, and dividing it by the mass, and that tells you omega squared. Whoops. So on here, I'm just going to make me a little bit smaller. Can't make myself that much smaller. We've got some of the key points, and in fact I'll share this with you later, but realizing that omega squared is equal to k over m. Now with all of this information, you can approach any simple harmonic motion problem as long as it doesn't involve energy, because that's what we're going to do next. But I'm going to give you some questions on Google Classroom to complete, and we will go through those in class later. Have a good day. Goodbye, everybody.